This overview video focuses on sketching rules for root loci. So in the previous video we said briefly what are root loci and why are they important, and now we want to focus on how do I compute root loci. We want to sketch the root loci by hand, okay? Because in practice we want to be able to do this quickly, should we say in 30 to 60 seconds. And why do we want to do that? Because if you can do a sketch, it basically gives you valuable insight that you can use in design. And you'll see we're going to use very simple feedback loops for this analysis, because most loops can be reduced to this form anyway. Negative feedback. For convenience, assume that the closed loop transfer function can be reorganized into the following format. So the key point is, if we had a compensator M and a system G, we're going to combine those into this form here, some scalar constant K times N over D, where N has got, is a function of S and D is a function of S. Now, why might we do that? Because it means we can now write explicit expressions for the closed loop transfer function and the closed loop pole polynomial in terms of K, N and D, and it keeps things nice and simple. Now, where are the closed loop poles? Closed loop poles can be given from many alternative definitions in addition to the pole polynomial. We get things like gk equals -1, the argument of gk is 180, and so on. Now, I'm not going to dwell on that, but the key thing is these different definitions are useful for defining different aspects of a root loci plot. So if you study this in any detail, you will see how these come up. The sketching rules then. The sketching rules are very simple. I've got to emphasize that. They are very simple. They're quick to use, but they're worth the effort because they give you good insight with minimal hand computations. Now, I must emphasize that over and over again, minimal hand computations. There are a lot more than 5 rules in the book, but in my view, the extra rules are not as simple, and so I would not bother with them, not by hand. If you really need an accurate plot, use a computer. So rules 1 and 2. Where are the open loop poles and zeros? And hopefully you look at examples like this and you say, yeah, I can see the poles are at 0, 1, -3. There's no zeros. For this one, I can see the poles are at 0, -0.3, -0.2, and I've got a 0 at -5 and -1, and so on. And hopefully you're quite comfortable doing that by inspection. So, rule 1. What happens when this parameter k goes to 0? So you'll see I've written out the closed loop pole polynomial here. It's kn plus d. So what happens if k goes to 0? The poles are given by kn plus d equals 0. If k equals 0, then you'll see this reduces to solving d equals 0. So d is the open loop poles, and so you end up with this big conclusion: loci must begin from the open loop poles, because if k equals 0, your closed loop pole polynomial reduces to d equals 0. Now, it's conventional to mark open loop poles with a cross symbol. What about rule 2? What happens as k tends to infinity? Well, again, you notice the poles are given by kn plus d equals 0. If k goes to infinity, then either the poles have to be infinite or n must be going to 0. So in other words, n equals 0 defines attraction points for the closed loop poles with large k. So some of the loci must finish at the open loop zeros. Now, I've done this very quickly. If you want a slower derivation and explanation, look at the slower resources on the website. And it's conventional to mark open loop zeros with a 0 symbol. So here's an example of rules 1 and 2. Mark the start and end points on the root loci for the following system. So rules 1, basically, where are the open loop poles? And mark them with an X. And you can see for this system, the poles are at 0, -1, and -2. Rule 2, where are the open loop zeros? Well, here they're at -1.5, mark them with a 0. So that's rules 1 and 2, and hopefully you'll agree that can be done very, very quickly. Rule 3, asymptotes. In general, there are more poles than zeros. So where do the excess of poles over zeros go as k tends to infinity? And for this example, you can see there are clearly 3 poles and 1 0. So the excess of poles over zeros is 2, and that means we're going to have 2 asymptotes. So in more general terms, if there are k poles and m zeros, the excess of poles over zeros is k minus m, which means there are going to be k minus m asymptotes. The other m poles go to the open loop zeros. They're called asymptotes because some of the poles approach infinity as k approaches infinity, and the asymptotes show how the poles approach infinity. So asymptote directions. Basically, it can be shown that the asymptote directions come from the k minus nth roots of minus 1, which you'll see what I've put down here. So if k minus m equals 2, you get the square root of minus 1. If it's 3, you get the cube roots of minus 1. If it's 4, the fourth roots of minus 1, and so on. Now, I'm not going to derive these, I'm just going to give the answers. The key thing you really need to know is what are the directions. So you can see if k minus m is 2, the asymptotes are plus or minus 90 degrees. If k minus m is 3, the asymptote directions are minus 180, plus or minus 60. If k minus m equals 4, you get plus or minus 45 degrees, plus or minus 135 degrees. And to be honest, you're not likely to get pen and paper examples beyond that. So here's an illustration. What are the asymptote directions? So for this one, I can see that k equals 3, there's 3 poles. M equals 0, there's no zeros. So k minus m equals 3, that means there's 3 asymptotes. So the asymptote directions are 180 degrees and plus or minus 60 degrees. For this example down here, once again, k equals 3, there's 3 poles, but m equals 1, there's 1 0. So k minus m equals 2, so the excess is 2, and therefore the asymptote directions are plus or minus 90 degrees. Now just a quick warning here, the asymptote assumption assumes that the maximum power of s has a positive coefficient in both the numerator and the denominator. So the numerator and denominator are expressed in this form. If you have a factor a minus s, you're going to need positive feedback rules, and we cover that in a different video. Rule 4 then. Where do asymptotes leave the axis? And it's key that we look at this because asymptotes and loci are not the same thing. And where the asymptotes leave the axis is useful information because otherwise we're not going to put the asymptotes in the correct point. And finally, just to re-emphasize, loci approach asymptotes asymptotically, not necessarily for low values of k. So here's an example just to illustrate the point. You can see the asymptotes are put here in dashed lines, and the centroid of the asymptotes has been marked here. And you notice that centroid is actually not on the loci. It might be, but it doesn't need to be. And you can see here that the loci approach the asymptotes asymptotically, but not necessarily for small values of k. But we need the centroid to put the asymptotes in the correct place. So where do the asymptotes leave the real axis? We have this formula here. Very simple formula. The sum of poles minus the sum of zeros equals k minus m times the centroid. Now there's an indication here of where that rule comes from, but if you want to see the derivation slowly, please look at the website for the slower resources. So here's some examples. Find the centroid for the following examples. So first mark where the poles are. So the poles are at minus 1, minus 2 and 0, and the zeros at minus 1.5, and then we use the formula. Sum of poles minus sum of zeros equals k minus m times the centroid, and so you get minus 3 minus minus 1.5 equals 2 times the centroid, which in this case is going to give you the centroid equals minus 1.5 over 2. And hopefully you say, yeah, there is a bit of computation there, but it's not particularly challenging. Now for this next example, we can show once you get familiar with the formula, you can actually write things down fairly quickly. So the sum of the poles in this particular case is going to be -6 minus 2. The sum of the zeros is -4. So you put the formulas together and you're going to get -8 minus -4 equals 3 times the centroid, because k minus m is clearly 3 for this case. And therefore, -4/3 is the centroid. And hopefully you're happy. Yes, that rule is probably the hardest rule in terms of computation, but it's still fairly quick. So the next few slides are going to look at rule 5. Where are loci on the real axis? And here's a summary of how you do it. Imagine you could sit on the axis, look to the right and count the number of poles and zeros you can see. If that number is odd, that part of the axis is on the loci. So let's show you where this rule comes from. Basically, it comes from this argument rule. I'm not going to dwell on that. That is a closed loop pole if the argument of kn/d is -180. And let's show you how you do it in practice. So here I've marked all of the poles and zeros with crosses. There's only poles in this case. So number 1, sit on the axis. So there's my person. It's standing, but you can imagine they're sitting. They're sitting on the axis. And key thing is, you can see I'm looking right. Okay, so look to the right. Now, if you're only looking right, how many poles and zeros can you see? So what you'll see is the person stood there, they can see just one pole. They can only see this one. Because that is an odd number, you'll see what I've marked. I put yes, it's an odd number, so that means this part of the axis must be on the loci. Now let's move to this bit. If they stand or sit in this bit, they can now see 2 poles, and so that's an even number. It's not on the loci. If they stand on this bit, they can see 3 poles. It's an odd number, so it means all this part of the axis, all the way to -infinity, is on the loci. And finally, you can see if I go to the far right, I can see 0, which is an even number, so it's not on the loci. And here's a different example. You can see with lots more poles and zeros, and you can see in this region here, if I look to the right, I can see either 1 or 3. That's because we've got this complex conjugate pair. They always come in pairs, so they don't actually affect the counting. And you can see in this bit I've got 5, which is an odd number. So you just use hashes or something to indicate the part of the axis which is on the loci. Okay, so just a quick example. Which parts of the axis are on the loci? So I do a quick plot here, mark the poles and zeros. So I've got a pole at 0, I've got a 0 at -1, a pole at -2, a pole at -3, and a 0 at -5. So there's where all my poles and zeros are. And now I just need to look at which bits is there an odd number to the right. So in here it's 1 to the right, that's on the axis. In here it's 3 to the right, that's on the axis. In here it's 5 to the right, that's on the axis. So I put numbers there if you like, 1, 3, 5. So it's as simple and quick as that. So a summary of rules 1 to 5 then. Mark the open loop poles with a cross. Mark the open loop zeros with a 0. Compute the asymptote directions from the excess of poles over 0, and you can just do that by memory. Compute the asymptote centroid, and then add the asymptotes to the plot, and that's the only bit that actually requires some computation. And then add the parts of the loci on the real axis. And hopefully you all agree these rules can all be done very, very quickly. So it's a back of the envelope sketch, something you can do very quickly. Now, I do not recommend students do precise sketches, or if you like, plots by hand. Consequently, I'm not going to cover breakaway points within a sketch. I'm not going to cover departure and arrival angles. These issues require tedious numerical computations, and if you're going to spend the time doing that, you might as well turn on the computer and let the computer do the job for you. If you want more information on these more advanced rules, then look in the textbooks, but as I say, my point of view is that with modern computing, there's no point doing it by hand. Some numerical examples then. The best advice is just to go through rules 1 to 5 in order, marking down what you observe. And soon you'll find you have the sketch done in literally seconds. And we'll illustrate this in the following examples. So first example, you can see rule 1, where are the open loop poles? You see I've marked them with crosses. Rule 2, where are the open loop zeros? In this case there's no open loop zeros, so there's none marked. Rule 3, what are the asymptote directions? Well, the excess of poles over zeros is 2, so the asymptote directions are plus and minus 90 degrees. Rule 4, where is the centroid? So for that, remember you need the sum of poles minus the sum of zeros divided by 2. So in other words, minus 3 over 2, and you can see the centroid therefore is here. And then you sketch on the asymptotes, which in this particular case happen to overlay with the root loci. Rule 5, where is the real axis on the loci? Well, in this bit here, I've got an odd number to the right, so that's on the loci. And that's it. For this example, I'm done. Example 2, slightly more complicated. You'll see it's a cubic up here in the top right. So first, where are the open loop poles? Well, they happen to be, you can see, at -1, -3 and -5. So I've marked those for you. Mark the open loop zeros with a 0. There's no zeros, rule 2 done. Compute the asymptote directions. Well, for this one, you can see that k minus m is 3, so therefore the asymptote directions are 180 degrees and plus or minus 60 degrees. Compute the centroid. So I'm not going to put the calculation, but again you see it's sum of poles minus sum of zeros divided by 3. You can see the sum of poles here is going to give you -9. -9 over 3 is -3. It's very, very quick. So now I can actually add the asymptote. So starting from -3 and making sure that that angle is 60 degrees. So again, you can do that approximately very, very easily. And finally, rule 5, add the parts of the loci on the real axis. So there's an odd number to the right in there, and there's an odd number to the right in there. And so what you can see is these two come together, they join, and then they go towards those asymptotes. Right, now example without any figures to help, because this is more realistic of what you might get in an exam. So first thing to do, draw some axes, but remember this is a sketch, so you see I'm going to do this very, very crudely. Where are the poles? There's a pole at the origin, there's a pole at -1, there's a pole at -4, rule 2, there's a 0 at -2. So that's rules 1 and 2. Right, rule 3, how many asymptotes? Well, k minus m is 2, so I'm going to get plus or minus 90 degrees. Rule 4, sum of poles minus sum of zeros divided by 2 is going to give me -5 plus 2 over 2, which is -1.5. So if I use a blue point, it means the centroid is going to be there. I'll now put my plus and minus 90 degrees. So there are my asymptotes. Okay, and then rule 5, where is the real axis on the loci? So I've got an odd number to the right in there, and I've got an odd number to the right there. So what you can see is that pole is moving to the right and going to that 0. These two poles come together, join, and then go off to the asymptotes. And hopefully you agree that sketch did not take very long. Okay, and it gives me a clear indication of what is going on without having to spend 5 minutes booting a computer. All right, this last example is a bit more complicated, but just again to illustrate the point that you can do this quickly. So draw some axes. So we've got a pole at the origin, we've got a pole at -1, and this s squared plus 2s plus 5 gives you poles at -1 plus or minus 2j. So you've got 2 poles there, and you've got a 0 here. So that's rules 1 and 2. Rule 3, k minus m is 3. So the asymptote directions are -180 and plus and minus 60. Okay. Rule 4, where's the centroid? So the centroid is going to be -2 minus 1 plus 4 divided by 3, which is 1 over 3. So the centroid is actually in the right half plane. So the centroid is here. So I now do my plus or minus 60 degrees. There you go. So there's my asymptotes. Rule 5. Which parts of the axis are on the loci? I've got an odd number to the right in there and an odd number to the right all the way over there. So now your headache is, okay, what's going to happen? Now it's not entirely clear by hand. So here you're going to have to do a bit of estimation. It's not an easy example, but probably what's going to happen is that these two will come round like this. Then one will go that way and one will go that way. And these two will join and one will go off that way and one will go off that way. And again, you see the point. You can get an impression of what's happening very, very quickly. So a summary. We've introduced the 5 rules for sketching root loci and given a concise explanation of the origins of the rules. The key points about a sketch chart: it must be quick, otherwise you might as well turn on the computer. And the main purpose of a sketch is to aid insight and understanding, and we're going to use that when we move on to controlled design. As ever, if you want an accurate plot, use a computer. Personally, I find it difficult to argue a reason for doing tedious pen and paper exercises our forebears had no choice but perform because they didn't have computers.